Yeah, I'm up there.
Think we got lucky as hell.
That
That lobby was like this, or if
yeah.
it was like that,
would have been bad.
we probably 3 days into it.
Yes, that stinks. Come on in, everyone. We got about 1 minute. I'm gonna go turn the TV down. Actually, can you go turn the TV down for me, Greg?
Yeah.
Yes, appreciate that. Anybody have any questions while you're waiting? Should be by end of the couch or oh yeah, by June.
Good.
Yeah, thank you. Appreciate that. So no questions, I take it. There it is. That's actually a good question, Ethan. I chapter 21 and 22 I meant to open already, but I didn't. So I'll definitely open it up. Actually, let's see if I'll do it right after class. And not only that, we're going to have our face-to-face exam was supposed to be Thursday. Of course, that's July 4th, so we're off. I don't want to do it Tuesday, so I'm not planning on getting your lab teacher to do it then. So what I think I'm going to do is make another attempt to do it online with, again, you guys can use a mirror just like last time. If I find that it looks kind of sketchy or even I have a little bit of doubt, I have to make you retake it at the testing center or with me. But you can also take it at the testing center. But like I said, just ideally, I would have a mirror and your webcam as well as Respondus lockdown browser and Respondus monitor. So, but that's just for the face-to-face test. The practice test and the online test, I'll open them up really soon. And I'm planning on having the actual test, the face-to-face test. I think I'm going to open that up right after midnight on Wednesday, early Wednesday morning, which is the early Thursday morning. And you'll have through Friday at 11:59 p.m. to do that. So anybody else have any questions?
Do you have an example photo of what the setup should look like for the test, like the mirror thing? I'm a little confused.
Yeah, I posted a picture of that on it's actually in Canvas on the important documents and links page. But basically, if you imagine this is my computer monitor, what we would ideally want is something like the computer monitor being at this angle and the student possibly being at this angle and the camera being basically where my camera is. The point being right here would be the desk surface and right here would be the person's lap. So the mirror allows me to look through that camera out at the mirror and see your workspace and see if you're, for instance, spending too much time staring into your lap or staring off into space behind your monitor or something like that. Ideally, I want you to have that mirror, and the bigger the mirror, like I said, up to like 8 by 12 or something like that, the better it is. But you're not, I never specify that you have to have it like in your syllabus or anything. But there is some chance that if your eyes are looking sketchy or something like that, I might, for no real good reason, make you retake it. And of course, it'll be a slightly different test, but you'd retake it at a testing center or with an actual proctor like me or something like that. But if you don't have one, like I said, you can still actually take it without the mirror. Just there's some chance, like I said, I'll look at the video and say, no, I can't accept that because it gives me dings and stuff like that. It records the whole thing, and not only that, it lets me know when you're taking it, so I can in principle come in and look through your window or through your computer camera at any time you're taking it. So please dress appropriately, that kind of thing. But the main thing is because I can do that and because I can see through there, that actually hopefully keeps you guys from putting stuff on your that you're not supposed to bring in and that sort of thing. So that's what the mirror's for. I would really prefer it to have the mirror, but if you don't have the mirror, you can still do it on your own at home. It's just there is a probability that I will look at it and just deem, even though there's not 100% proof, or not even, maybe not even 50% proof that you cheated or something like that, and I might make you retake it. So just be aware of that. That's all. Anybody else have any questions? All right. So, you can't take it in lab. Your lab, doesn't your lab meet on, it does meet on Thursday, right? Well, Thursday's is July 4th and classes are off, and this college is closed that day. That's why we can't take it that day. And I really don't want to push it further back. So hopefully that'll help. Anybody else have any questions? Sorry, I'm taking a snapshot of the roll again just to make sure I have it, because I haven't found my roll sheet where I put it away when we were working on my office. Sorry about that. Let's see, I've got it here. Okay, I got that anyways. All right, so when we last talked, we had worked out some stuff. I remember I made a really bad, I shouldn't even say careless, but a really bad mistake when I was first starting off, namely because I started off with the formula for the calculation of the change in potential energy as opposed to the change in voltage, and then somehow I just transformed it into the change in voltage. So that first part's really bad. I thought about actually just cutting that part out of the video, but I really don't want to be dishonest. I don't mind my students knowing I make mistakes. I mean, that's part of the learning process for you guys to realize you're going to make mistakes. But that being said, just remember that opening part's not very good. The main thing you need is the result, and I'm going to say it out loud here, which you'll see as an equation in your book. I don't remember the equation number, but basically it is that the change in potential energy, which we call delta U, which is U final minus U initial, we're calling that UB minus UA, meaning the final position was a distance RB and the initial position was a distance RA away from the origin. So delta U is equal to UB minus UA is equal to the negative of the work done, and that's written as W sub BA. Okay. That is something that we will use, and that's sort of the method that we use to determine what a potential energy function is. So we can imagine the actual conservative force. That's why the negative sign on the work there. We can actually imagine the conservative force doing the work in taking the particle from A to B. And when we calculate that work, we multiply it by a negative, and that gives us a change in potential energy. That is essentially exactly how we got the formula mgh for the potential energy of a mass some distance h above the surface of the Earth. Okay. Now, that was also under the assumption that G is a constant, and G really is a constant for a fairly large range of heights above the surface of the Earth and depths below the surface of the Earth. But still, it's not exactly perfect. So when you do that more fully, you have to use the gravitational acceleration formula, which is capital G, the mass of the planet divided by the square of the radius of the planet. That's the really one. That's the real G as opposed to 9.80. And when you do it that way, then you get a more general formula, which is negative Gm over R. Okay. So that's the actual just potential energy, not change in potential energy. But that's how we could do delta U, or that's how we could use delta U to calculate what U, the potential energy, is. Now, the other equation was the change in voltage, delta V. Delta V is equal to VB minus VA, which is equal to V sub BA, which is equal to, and here's the part where it changes, UB minus UA, all of that divided by Q. And then that's equal to negative WBA over Q. And that's equal to the negative integral of E dot DL. Notice I said E dot DL, not F dot DL. Those are the main results we need. And that's what I'm going to use. And that's what, we've derived basically in the other attempts. So we're going to start from there and solve some more problems. Anybody have any questions on any of those problems? They're in the equation sheet that I gave you guys. It's accepted for this whole semester. So that's a good place to look if you lose track of them. Now, let's go on. I'm actually looking through, for instance, through chapter 23 and looking at various examples as well as looking at various derivations to try to figure out, what is the bare minimum number of examples I need to work for you and how many examples I can fit in for you. There's different levels and intensities that we can cover the course material at, and I try to keep it at the appropriate level, but at the same time, I also try to give you some of the hardest examples, and I skip a lot of the quote unquote easy examples. So like when we did electric flux, I didn't care to do a calculation of E dot A for the special case where E is a uniform electric field and A is a flat surface, because that's just really rudimentary. But I did, show you some cases of E varying as a function of position and then the surface being a non-flat surface. So hopefully that helped. Now I'm gonna go ahead and share my screen and remind you what those formulas are. So what the formula can be, for instance, I know it's still loading, so don't worry, I'm not leaving you behind or anything. What we found was delta U is equal to UB minus UA, which is equal to the negative of the work done in going from A to B. And that's equal to the negative integral of F, excuse me, so I almost made the same mistake I did at the beginning of class last time, F dot DL, and that's from RA to RB, okay? Now remember, it's the line integral, and what we warned you about the line integral is you technically have to make the F dot DL be evaluated specifically on the line or path you're integrating along, and the DL or the range of integration, one of the two has to correctly identify the direction you're going. So for instance, if I'm going from x equals 5 to x equals 3, then I could indicate that by integrating from x equals 5 to x equals 3. And if I chose to do that, then the DL is just going to be dxi hat, because that's the positive coordinate direction. If I wish to indicate the direction using the DL, then I would have written DL is negative dxi hat, and then I would have integrated from 3 to 5. Okay, so that's the big rules about path integrals, line integrals. Now, in addition to that, there's another formula that's a little more useful, so I'll put this one in blue, and that's delta V, which is V from A to B, which is the V of B minus the V at A. That is in fact equal to, I will take this time to write this, UB minus UA, all of that divided by Q, okay? And actually I should have put that Q in the center. Okay, I was thinking about what I was writing next, that's why I put it off to the side. And this is in fact equal to the negative of the work done in going from A to B divided by Q. And because you're dividing that by Q, the integral F dot DL is going to become E dot DL. So I end up getting negative integral E dot DL. And looking at this, you can see, in fact, that VA is equal to UA over Q. And what we found was, for instance, that the voltage at, let's say, R is equal to Q over 4 pi epsilon naught R, specifically for the voltage due to a charge Q at the origin. So I'll say this is the electric potential at any point a distance r from the center of charge will of the charge Q. However, R should be greater than the size of Q. In other words, if for instance Q is a spherical charge distribution, then you want to make sure the radius, which is, since it's spherically distributed, the center of mass, or excuse me, the center of charge of the charge Q would be at the center of the charge. You want to make sure that you're only calculating voltages or electric potentials at a distance greater than R away, because this is just done as if I integrated out from infinity, where I set V equal to 0, and integrated into R where I'm still outside of the body. So specifically, R has to be a distance that puts the point outside of the physical body of charge Q. So that's why I had to add that note, just to let you know. But that's some of the stuff we will be using. So does anyone have any questions on that? So for instance, your book makes a nice point of this. So I should tell you that if you actually want to plot voltage versus radius for a positive charge Q, then this equation will look exactly like this. Okay, where for instance, oops, actually I'll just leave it like that. But I will stress that this formula falls off like 1 over R, because the formula is in fact V is equal to Q over 4 pi epsilon naught R. Now, if we go further and say, I would like to calculate the voltage due to a charge negative Q, then what we get is a very similar graph, only it looks like that. And again, this is proportional to 1 over R, and specifically the voltage is Q over 4 pi epsilon naught R. So any questions on that? The big thing that you're supposed to notice here is that force and electric field fell off like 1 over R squared. But voltage falls off like 1 over R. And this is all true, of course, for point charges. So spherical charges, because remember, we basically can show, or Newton actually did show with the law of gravity, which has the same form as this, showed that basically if you have a spherically symmetric distribution of mass, then you can treat the mass causing the gravitational field as if it were a point particle at the center of mass of the spherical distribution of mass. Similarly, we can say the same thing about the distribution of charge at the and the voltage for it. Okay, any questions on that? Okay, so the last example we worked was one very much like example 23.6, which is basically the work required to bring two positive charges together. And your book talks a lot about this. This is something that's kind of important. But when you bring the first mass in, let's say you have a charge Q and it's out infinitely far away, and you want to bring it into some distance, or maybe even you want to bring it to the origin. It doesn't really matter. The main thing is when you bring that one in there, if there's no existing electric field or no existing charges in place, then there is no electric field. And bringing in that first one doesn't take any work or energy whatsoever. So you have that, and it's not a big deal. But when you go to bring in a second one, that first one has established an electric field and therefore also established an electric potential. And it's going to take some work to bring in the second one. And we were asked to calculate the work required to bring two positive charges close together. What also happens, though, is if you wanted to build up, N charges, then you're going to have let's say the 15th charge is going to come in, and it's going to have to deal with the electric potentials and the electric fields created by particles 1, 2, 3, 4, 5 on up to 14. And then when you bring in the 16th, then it's going to have to deal with particles, their electric fields and their potentials up to the charge number 16, so on and so forth. And it's very easy to write simple little sums and stuff like that. The summation of VI1 or V sub IJ, okay, where the voltage is the voltage of J due to I, or I due to J, or something like that. It's really easy to say that, but you got to be careful, because when you do a sum, it's very likely that you're going to count V12 and then also V21, but that would be double counting. So you got to be careful for that with that. And your book talks a lot about it. So I'm not going to put too much work into it, but I do want you to think about such things when you go to answer questions like how much work does it take to build this assemblage of charges? And in an example in the book, it's also asking us to do something like one of the first problems we did with Coulomb's law. So I'm going to do something like that. So let's say example. So in this case, what I would like to do is calculate the electric potential at two different points. And I have a very specific diagram in mind. So let me first draw the diagram, and I'm going to go ahead and use a coordinate system. Remember, the coordinate system is something that I put in as an instructor, but in reality, when you're solving a physics problem, unless they explicitly give you the coordinate system, you're required to make your own. The advantages of them giving you a specific one is it's a lot easier to make, for instance, a multiple choice question, because then everybody agrees what coordinate system we're using, and the answer has to be a very specific answer. So some of these times they're not going to give you a coordinate system. You got to make up your own. So that's what I'm trying to say is, yes, I draw this for you almost every time, but be aware that sometimes you're going to have to draw your own. What I'm going to do is I'm going to imagine there's a charge over here that's going to be negative Q, and that's going to be negative, let's say 1.111 times 10 to the negative 10th coulombs. And then, and then this one is going to be positive Q, where Q is equal to one. Well, actually, I probably need to write this somewhere else. So let me do that. I'm going to write the positive Q somewhere else. So I'm going to say positive Q is equal to 1.11 times 10 to the negative 10th coulombs. Okay. I'm going to say this is specifically at, let's say, 3.00 centimeters, and this is specifically at negative 3.00 centimeters. And I'm going to say that this is the charge and this is the charge. Now, what I would like to do is go up here to, actually, let's make those 4, since I did draw it on 4 blocks, it'll just make it easier. So let's change this 3 to 4. Oh, I guess I'm just gonna write that in blue now. Okay, I'm changing that to 4. And I'm changing the next one to 4 as well. So let's see if we can do that. My dogs are so helpful. Okay, and then what I'm going to do is go up here to 3. And what I will do is I'm going to say, this is the line y equals 3, so it's easy for me to find. And what I'm going to do is calculate, that's P sub A. And then right here, that's going to be P sub B. And what I want to know in this problem is what are the electric potentials at PA and B at PB. So that's the problem we're trying to solve. I'm going to write solution. And what we're going to see is, remember that the formula we're going to use is V is equal to Q over 4 pi epsilon naught R. That's the formula for a potential due to a charge Q, a distance R away, assuming the distance R is big enough to get you outside of the body of Q. In these cases, I'm dealing with point charges. So now I'm going to go ahead and write down for part A, we're going to say the voltage at A is equal to the voltage at A due to the negative charge plus the voltage at A due to the positive charge. Okay. So the voltage at A due to the negative charge is, of course, 1.11 times 10 to the negative 10 coulombs divided by 4 times pi times 8.85 times 10 to the negative 12th. And that's Newton, or excuse me, that's Coulomb squared per Newton meter squared. And then I've got to figure out the distance between the negative charge and the positive charge, and the point A. So the distance you can see is a horizontal distance. If I go from the negative charge, I got to go a whole 8 centimeters. And then I got to go up another 3 centimeters. So, and the distance has to be to the first power. So I'm going to go ahead and write it as a square root, and 0.0800. Now that I've put it that way, it's actually in meters, plus 0.0300 meters, and that's going to be squared as well. Now, that's just due to the negative charge. Now, due to the positive charge, we're going to have more or less the same formula, but this time, oh, and I forgot to put the negative charge in there, sorry. This is one case I really want to reiterate that. Remember when I told you Coulomb's law, F equals K, Q1, Q2 over R squared? You generally, I advise you not to put the signs in. I agree with that. The electric field, K, Q over R squared, don't put the signs in. I still agree with that, okay? But in the case of voltage, these are not vector quantities. These are just scalars. So the negative sign is very important. You add these like positive and negative numbers, not like vectors. So the negative sign being put in there is absolutely essential, whereas the negative sign being put in the vector formulas can often just make it more confusing and make it where you have a difficulty deciding what the X component is and the Y component. So I do recommend putting them in here. And now that I learned how long that fraction bar is, I'm going to put this one way over here. Now, you might notice the number 1.111 times 10 to the negative 10th is really 1/9 times 10 to the negative 9th, basically. So that was essentially K, which was 9 times 10 to the 9th. So in doing so, I'm trying to actually cancel out the nastiness of 4 pi epsilon naught. So that's why those numbers that I chose seem a little weird. Oops, it's capital Newton meters squared. And now I've got to multiply this times the distance away. So when we're talking about the distance away between the positive charge and the point A, that distance is just 3.00 centimeters. So now that I've centered up this number, I don't really need it to be centered up because I'm a dummy. Okay. Anyway, so 0.0300 meters. And that's the whole distance. So now I can compute this, and the way I do so is negative 1.11 e to the negative 10 divided by, now I'm going to say parenthesis 4 times 3.14159. It's better if you have a pi button. I have a pi button, but it takes a lot of crap to get to it. So with this calculator, so I'm not doing it. So I said 4 times 3.14159 times 8.85 e to the negative 12th times, now I'm going to put in a square root. And this square root is going to be 0.08 squared plus 0.03 squared. And when I put in a parenthesis, when I put in a square root with my calculator, it automatically gives me a parenthesis. So I'm closing off that parenthesis, and then I'm closing off the parenthesis that I had for the actual denominator. So I just did the first term. I'm going to write it down so we'll have that. This is negative 11.6817, and that should come out to be volts. And now I'm going to add to it the result due to the positive charge. So that's 1.11 e to the negative 10 divided by parenthesis 4 times 3.14159 times 8.85 e to the negative 12th times, now this time it's just going to be 0.03 and close parenthesis, and this time I get 33.2697, giving you way more sig figs than necessary. And that should be volts as well. What I'm going to check is 0.08 squared. That is 0.0064, and 0.03 squared is, of course, 0.0036, or excuse me, 0.0009. I was don't yeah, just ignore me. Okay, so 0.0009. So what that tells me is I'm really going to have only access to, when I add those two, would be to the 3rd, 4th, and 5th decimal place. So only the 3rd, 4th, and 5th decimal place come out of adding those two numbers. So when I do that, I get 0.00730. So there's 3 sig figs there. Now I'm going to take the square root of that. Oops. and that gives me 0.0854. So again, I've got 3 sig figs. So it does look like everything's going to be 3 sig figs, no problem, which means I only know these numbers up to 1 decimal place. So now I can go ahead and add these two numbers. I'm going to say 33.2697 minus 11.6817, carrying way more digits than necessary, obviously. And this is going to give me 21.586, or excuse me, 588. But as we said, we had 3 sig figs, so that meant only the 11.6 and only the 33.3 essentially were valid. So I only have 1 decimal place that's a significant figure. So these two are not significant figures. So I'd actually call this 21.6 volts. But notice how much easier it was to compute this than it was when we did Coulomb's law, because we had to break all that stuff into vectors. That's part of the beauty of the electric potential, is we're not using vectors. Before I do part B, does anybody have any questions on this? Okay, looks like we're good. Actually, let me double check my chat. I don't have the chat window open. Now I do. Gotcha. All right, so I have the chat. So if you have questions, you can type there, but let me know, because I won't necessarily see it out the corner of my eye. Now, in this case, we're going to do for the point B, which is right there on the y-axis. Everybody sees it right there. So that's dead center between the two charges, but up above by 3 centimeters. So in this case, we again get VB is equal to VB due to the negative charge plus VB due to the positive charge. And that's going to be, of course, in this case, both of them are going to be square roots, but in this case, both of them are going to be a part of a 3, 4, 5 triangle. So the square root is going to be really easy. In this case, the negative charge is the one on the right. So that's going to be negative 1.11 times 10 to the negative 10 coulombs. All that's going to be divided by 4 times pi times 8.85 times 10 to the negative 12th coulombs squared per Newton meter squared. And then the distance, since this distance right here is 4.00, and this distance is 3.00, we see that we have the 3, 4, 5 triangle, which means this distance is 5.00 centimeters. Okay, so I'm just going to put 0.0500 meters in the bottom. Now, because this is a much smaller fraction, I can afford the time to write in 1.11 times 10 to the negative 10 coulombs over 4 times pi times 8.85 times 10 to the negative 12th coulombs squared per Newton meter squared times 0.0500 meters, like that. Now, I squished everything in there, but I'm going to zoom in so you'll see it. It's 1.11 times 10 to the negative 10th divided by 4 times pi times 8.85 times 10 to the negative 12th times 0.0500 meters. Now, the reason why I don't care too much is because it's obvious now that these two numbers are equal but opposite, because the left one is a negative sign and the right one has a positive sign. So the voltage at B is in fact 0 volts. You'll notice that's also consistent with your field mapping, which hopefully if you did your field mapping, one of the things you mapped was a point charge and a point charge. And 1, 2, 3, 4, 5, 6, 7 is how many I've got across here. So if I went dead center between them, what I would find is a potential of 0 dead center. So that's what we're really looking at here. And then, of course, if I went to this side, it would be something different and do like this, and then something different and do like this, and then something different and do like this, so on and so forth. That should be completely symmetric. But the main thing we're seeing here is dead center between the two, there is a voltage. And technically what they're doing, what we're going on the assumption is that there's essentially like a negative voltage on the right hand side and a positive voltage on the left hand side that are both equal in magnitude, but one's positive and one's negative. So dead center between them would give you a 0 volts. That's sort of the assumption that's going on. That's how we got the 0 volt for answer B. Anybody have any questions on that one? Okay, look pretty good. Your book actually gives us a nice conceptual example. I want to read over this and see what you think. It says, consider two isolated charges, Q1 and Q2. This pair of charges is shown in three different configurations in figure 2313, which set has a positive potential energy. Part B, which set has the most negative potential energy. Part C, what set requires the most work to separate the charges to infinity, and assume that all charges have the same magnitude. So that's what we're looking at for this example. So I'm going to say conceptual example. And this is specifically conceptual example 23-8. So I want to look at our figures, which is 2313. And these figures are surprisingly simple. We have a red charge and a green charge, like that. And then we have a red charge and a green charge. Oops. And a green charge like that. And then we have two red charges, which are essentially the same distance, but not necessarily. Now, what this is supposed to mean is the red charges are positive and the green charges are negative. And this is case 1, this is case 2, and this is case 3. And the questions were asked again is A, which set has a positive potential energy? And then for part B, we're asked which set requires the most, or excuse me, for part C, which set has the most negative potential energy? Notice I'm saying potential energy here in both cases. And then part C, which set requires the most work to separate the charges to infinity? So which set has would require the most work to separate them and actually separate them, take them all the way to infinity. And I've tried to, draw this somewhat faithfully. It looks like to me, as best I can tell, that the two positive charges in set 3 are slightly closer to each other than the two the positive negative charge right above it. It does look like I screwed up a little bit with one of these charges. So let me move. I'm going to move this just to make sure I'm consistent. I'm going to move that charge to right here. And then I'm just going to put the plus in there. So now I've got a full two charges gap between the left edge of the red top charge to the right edge of the red middle charge, and the same thing with the right edge of the green top charge to the left edge of the green middle charge. So that's what I was shooting for, to make sure it's sort of symmetric. Don't know why that's relevant other than I got OCD. So let's move on. So what we're asked is about potential energy here. That's key. We're not doing electric potential. Electric potential is the voltage, and that's something that's measured in volts, whereas we're talking about the kinetic energy. So we need to make use of our understanding of actual potential energy as compared to voltage. So for instance, one thing we know is potential energy. So I'm going to write this here and say solution. The one thing we know is the potential energy is, in some sense, Q times the voltage. That's one of the formulas we tend to use, but we also know that the change in potential energy, delta U, is equal to the negative of the work done by the conservative force. In other words, not done by some external thing or something like that. Okay, so we have that formula, and what we need to figure out is exactly which one of these does have, for instance, a positive potential energy. So the potential energy in this case, because I have it written like QV, you can see that U for part A is going to be, let's call these Q1 and Q2, which your book already had to some extent. So let's say this is Q1, Q1, Q1. This is going to be Q2, and this is going to be Q2. And by default, this red one down at the bottom, is Q2, but it's equal. Oh man. But it's equal. It's equal in magnitude to Q1, and magnitude and sign to Q1. So I just put that there to make sure we all were on the same page, because they did specifically and explicitly tell us that all the charges are assumed to be the same. Okay, so with that in mind, our potential energy becomes Q times V, and what we found our V was now in this case we're going to say Q1, and then V is Q2, say, over 4 pi epsilon naught times R, where R is the distance between charge 1 and charge 2. Okay. So since that's the case, we should remember that now that I'm using this formula, this is a place where they're specifically asking me not for a change in potential energy, but a potential energy. So they're saying specifically which set 1, 2, or 3 has a positive potential energy. So they're actually asking for the value of the potential energy, and therefore the signs completely matter. So I'm definitely going to consider putting the signs in. If I put a positive and negative in, then I get a positive times a negative gives me a negative. That's a negative potential energy. So that means positive times negative equals negative. And this implies 1 gives you v less than 0. And 2 will give you v less than 0 as well, because they're positive and negative. But the one that doesn't is 3, gives you a potential energy U is equal to negative, well, I'll just leave it at that. It's just 3 is the right answer. They didn't give us any numbers or anything like that, so I can't really express exactly what the answer is, but you can see that the R in this case is this itty bitty distance from here to here. Obviously, it's different in case 2, in which case it would be from here to here. And in case 3, it would be from here to here. So I'm trying to point to the center of mass anyways. Now we're going to do part B, and part B says which set has the most negative potential energy. So when they say the most negative, what they mean is I want it to be a negative value. So that means that I have to use case 1 or case 2, because those are the ones with 2 charges that multiply to give you a negative number. But then I also need it to be the biggest negative number. So can eliminate and now I'm feeling like eliminate has 1 L. Man, it's been so long since I actually wrote without a typing computer sort of thing. So it's really easy to make such mistakes. But anyways, we can eliminate 3 because positive times positive is greater than 0. Then we look for the largest magnitude. In other words, we want U to be the biggest distance on a number line from 0. I don't care if it's to the left or to the right. Specifically in this example, it has to be on the left, but all I care about is how big the size is. So if we look at 1 and 2, Q1 and Q2 obviously have the exact same magnitude as each other. So that's just going to be like a magnitude of Q squared in both cases. So that doesn't matter at all. What does matter is not the 4 pi epsilon naught, the Q1 and the Q2, but specifically only the R. So only the R matters. If R is very, very small, since it's in the denominator, that would make the numerical value of U very big. If R is very big, that would make the numerical value of U very small. Again, going on the assumption that we're talking about just the absolute value of the number. So if I want the absolute value of the number to be very, very large and negative, then to get the negative, I have to choose case 1 or case 2. And to get it very, very large, I need the R to be very, very small. So this tells me that my answer should be, in this case, 1. Because, and I'll say it like this, I'll say, because U is equal to Q1, Q2 over 4 pi epsilon naught R, and U1 is equal to Q1, Q2 over 4 pi epsilon naught times 1 over R1, and U2, that did not work out so well. U2 is equal to, again, Q1, Q2 over 4 pi epsilon naught times 1 over R2. Okay. Let's say I just look at this measurement and it looks to me like 1, 2, 3, 4, that it appears that R2 is on the order of 4 times R1. There's no reason for me to assume this diagram is actually to scale, so it's not even correct for me to say that it's 4 times R1. But what I do know is R2 is equal to some positive number greater than 1 times R1. Okay. So if I wanted to do U1 over U2, I could actually compute this. Now, I'm sort of what my friend would say, I'm nuking this. Okay. And that's not a compliment, by the way. That's if you're in the Navy, you know exactly what it means, I'm sure. But it means that I'm sort of overthinking it. And I am, but I wanted to make sure it's explicitly clear that I'm not guessing at this answer. This answer is exactly right. And here's how I know it's exactly right. If I did choose if I did choose the correct case, then this number that comes out should be greater than 1. The UI over U2, if the magnitude is actually bigger than for UI than it is for UII, then this number is going to come out to be a number bigger than 1. So now I can write it out as Q1, Q2 over 4 pi epsilon naught times 1 over R1. So I just basically wrote down the exact same formula that I already wrote above for U1. Now I'm going to do the same thing for U2, but instead of R2, I'm going to use that positive number greater than 1 times C1. So I'm going to call this number right here P. For no, P is not good. Let's call it let's call it G for greater than 1. Okay. Okay. So now I'm going to do that. I'll have in this case, I'm going to have Q1, Q2 over 4 pi epsilon naught. And then it's going to be 1 over R2, which, as I said, is in fact G times R1. So the reason I did it this way is now I can see that all this cancels out. And not only that, this R1 cancels out with this R1, and all I'm left with is in fact G on the top. And that, of course, is greater than 1. Therefore, oh, actually, let's do it with the typical. Therefore, U1 is greater than U2 in magnitude. Okay, so that basically is a definitive proof about us being right. Now for part C, it says which set requires the most work to separate. The work to separate really is trying to take how much energy it is to pull one mass out to infinity. And once you pull that one out to infinity, the other one's technically already infinitely far away. So what we see here is the work, which is actually equal to, like I gave you there, the negative change in potential energy. If I look at starting out in case, well, let's start off with case 3. With case 3, if I just let it go, if I didn't hold those charges down, those two charges are going to repel each other, and I don't have to do a darn bit of work to make them move apart. And in fact, the force is going to stay non-zero as long as the distance between them is less than infinity, which is always, right? So we're going to get the two in case 3 to separate all on their own, no problem. Maybe it might take a little work to make sure both of them are infinitely far away from the current spot. But the first one's going to be a freebie and the second one's just going to take maybe a little bit of work. I don't know, right? So we can go ahead and eliminate 3, but then it comes down to 1 and 2. Well, 1 and 2, the two particles are definitely attracted to each other. And since in case 1, they're really close to each other, that means the force of attraction is quite large. The force of attraction is what you're actually battling when you're doing the work. You're working against the force of attraction, and the force goes like 1 over r squared. If indeed particles Q1 and Q2 in case 1 are 4 times closer than they are in case 2, then the force of attraction between the two is 16 times larger than the force of attraction between case 2. So that automatically tells us we're going to use way more work to separate 1 than we are to separate 2. So the answer here is case 1 takes the most work. Any questions on that? Okay. And again, that's partly because they started off so much closer. It's going to take 16 times as much force just to start moving them apart at all. So I think that's pretty self-explanatory, and it looks like no one has any questions. So I'm going to move on to a little bit more. In section 23.4, they start to talk about potential due to any charge distribution. This is what I was talking about, how we're imagining bringing in different charges from infinitely far away and trying to calculate how much work it actually takes. Or more specifically, you can also calculate what is the electric potential of the charge distribution we have. So in that section, so subsection 23-4, what we get is some nice expressions. One we already knew, and that is the voltage due to a charge Q at a distance r away is 4 pi epsilon naught r in the bottom divided into obviously Q, right? Now using that, we can say or see that the voltage of a specific charge distribution V sub A is equal to the summation from I equals 1 to A of V sub I. Now, what's going to happen is the V sub I has a common factor of 4 pi epsilon naught in the denominator. And then what we're going to have to do is take the summation from I equals 1 to N. Excuse me, I said to A earlier. I don't know why I wrote to A. Let me fix that real quick. Oops. Let me just erase half of my sigma symbol. Okay. So in this case, it's going to be the summation from I equals 1 to N. But in this case, it's going to be Q sub I over R sub I. And specifically, what we're talking about here is the, let's say A is sort of like the first particle, or relative to some point A. So what we're going to do here is we're going to have R sub IA, which means the distance between the ith Q and the QA. So the voltage due to just the first particle A existing is basically going to cost nothing. But to bring in all the other charges, we have to compare the voltage difference but are the voltage due to the distance between QI with QA, say. So that's one of the formulas that comes in super handy when we're trying to build up a distribution. But the one I'm shooting for, as you might have guessed, is the one where we're going to do it with a continuum of charge instead of discrete charges. We're going to imagine that you can sort of smear the charges out over a distance. And if that's the case, then what we get is V is equal to 1 over 4 pi epsilon naught times the integral of dq over r. That really is the formula that we'd use, not unlike Coulomb's law, to find out what the voltage due to at a specific point, for instance, due to a distribution of charge. So let's look at an example with this. We'll call this, yeah, I guess this is example 3. So what I'm going to do is I'm going to imagine a ring of charge, and I'm going to put it in a coordinate system. Again, I don't have to do that. I do that for the work, and then you guys would just be given something like this. So here's my ellipse, and it really is supposed to be a circle, but it's in 3 dimensions and we're drawing it in 2 dimensions. So I had to show some foreshortening, for instance. So that's going to be a uniformly distributed ring of charge. Okay. And I'm going to imagine directly above its axis. In other words, there's a symmetry axis about which you can rotate this thing, and it will look identical no matter how small of an angle you rotate it through. And that point right above that and on that axis, that's where we want to know what the electric potential is. So this would be the drawing they give you, and they'd say something along the lines of a thin circular ring of radius r has a uniformly distributed charge, capital Q. Determine the electric potential at a point P over its center. Okay, that's more or less the problem. So when I come in to do this, I immediately draw a coordinate system because that's going to help me. I'm going to say this distance here is Z. And in fact, that axis is the Z axis. So that'll come in handy as well. And I'm going to say this axis right here is the Y axis. And this axis right here is the X axis. And I'm going to further illustrate that this distance is R and the total charge is Q. Okay. Uniformly distributed. So what I'm asking in this question is, what is the potential at point P above the center of a ring of radius R that has a total charge Q distributed on it uniformly. So that's the question we're asking. Okay. Now, since I did that, I'm going to go ahead and mark this as point P right there so everybody knows what we're doing. And I'm going to use my solution, which I shall do in purple. My solution is going to involve the fact that V is equal to 1 over 4 pi epsilon naught times the integral of dq over r. And remember, dq can equal lambda dL r sigma dA r rho dV. Okay. In this case, it's a very thin ring of charge, so I'm going to use lambda dL. And specifically, what I'm going to do is I'm going to draw this little line right here, which is out an angle theta. And then I'm going to allow that little line to move over by an amount d theta. And then this little sliver here is what I'm going to call dq. And that dq is going to be lambda times dl. And of course, the L is an arc length, so I'm going to call that lambda times r d theta. Now, since it's a uniformly charged ring, I know that lambda is equal to a constant. Okay, this is again because it's uniformly charged. And that constant is going to be the charge Q divided by the length, which is 2 pi times r. So now I know exactly what lambda is as well. So now what I'm going to do is start computing what the V is. So V is going to be 1 over 4 pi epsilon naught times the integral of lambda times r times d theta. And now I need to know the distance from dq to P. So I want to reiterate that as well. Distance from dq to P. So we're actually calculating the voltage at P. So that's the wording that you needed for that. So we can look right now and we see that this actually, in some sense, makes a right triangle. And you can see that one of the legs of the triangle has a length Z, and the other leg of the triangle has a length R. So if you realize that, and you just realize that this is a right triangle, then you know the hypotenuse is the square root of r squared plus z squared. And that's what I'm going to put down here, r squared plus z squared, like that. And that's the r that I have. Now notice the d theta is not affecting the r or the z or the lambda or anything. So this is like the world's easiest integral problem. I'm going to get lambda r over 4 pi epsilon naught square root r squared plus z squared times the integral d theta, and I'm going to integrate from theta equals 0 to 2 pi. So ultimately I get lambda times 2 pi r. You'll see why I wrote it that way, or in that order there. The integral of d theta is just theta, and then I evaluated it at 2 pi, so that's where the 2 pi came from. And then all this will be divided by 4 pi epsilon naught square root r squared plus z squared. Now, can anybody tell me what lambda times 2 pi r is, based on anything I've written or explained?
Not Q, or like the entire charge.
Exactly. It's the total charge Q. So we can ultimately write that the voltage at P is equal to Q over 4 pi epsilon naught square root r squared plus z squared square root of that. And that is the complete answer. Anybody have any questions on that one? All right, we can do another example. This time I'm going to do a charged circular disc. So here's example 4. What is I think I want to do it uniformly charged. Yeah, I think that's it. What is the potential a distance z above the center of a circular disc of radius r and total charge q that is uniformly distributed. So that's our big question. So let me go ahead and draw this guy. I'm going to make my disk. Go ahead, Funk, make my disk. So I'm making my disk, which is really circular, but I have to draw it elliptical because I'm looking at it in 2D and it's a 3D object. Okay, so there's my disk. I'm going to embed it in a coordinate system like I did before. The same orientation because that allows me to use letters like the Z and stuff like that. There's my y-axis. And there's my x-axis. And I am going to say that this particular disk has a radius r and a total charge q uniformly distributed. So what that means now, what that means is sigma is a constant. Okay. So here's my solution. I'm going to again make use of the fact that V is equal to 1/4 pi epsilon naught integral dq over r like that. You know that V is assumed to be calculated at some point P, and that R is the distance between the point P and the differential charge element dq. So in this case, I'm going to say right here is the point P, and in fact, that's a distance Z above. Okay. Now, you could like find a single differential charge element in the little disk, and as like some little RD theta would be one little rectangular slice. Like I could put it in. Let me draw this and then I'll erase it all in a second. But I want to show you what one of the possibilities would be if, for instance, you guys knew double and triple integrals and all that good stuff. What I could do is I could allow a line to sweep out an angle theta counterclockwise. I could allow the line to sweep out an angle theta counterclockwise from the positive x-axis, and that would go out some distance, little r, and then I could allow that line to wave over a little bit by an amount d theta. And then this little arc right here would be a distance rd theta. And what I could also do is let r change by an amount dr. So I'd get this little sort of rectangular thing. So if I did that, then dA would be r d theta dr. And that works fine, but you can see because I have a d theta and a dr, that's going to require a double integral. You're not required to know double integrals yet in this class, so I'm going to get rid of that. So here I am erasing it. You can take a screenshot if you want to hold on to this beforehand, or of course you can also just look at the video and draw it later. But basically what this angle was d theta, and what this distance was from here to here was lowercase r, and then that little area in there was r d theta dr. So that's really a typical way you could do that. And that would have a very specific r distance from the point P to that little dq. But if I had a single dq that had the same distance from the origin everywhere, and then of course straight up from the origin was a distance z, then I could sort of see that every part of that would have the same distance r, so I could use that. That's a way we can actually do this. So I'm going to go ahead and erase this. So let me erase all that red I just put on there, and let me create a more reasonable differential area element. And we're using a two-dimensional differential area element here, specifically because this is a two-dimensional disk. It's obviously three-dimensional. There's no, you can't really make a two-dimensional object necessarily in 3 dimensions. But that third dimension, the z dimension, is really, really thin. So what I'm going to do is I am going to draw another ellipse like so. Okay. And this ellipse is going to have a radius r. And then I'm going to allow it to have a finite or infinitesimal thickness dr. Okay, over on the sides, it'll look like it's a little bit thicker because we're seeing them in a way that it's not foreshortened. But in the front and back, it's going to be very foreshortened. So it's going to look really, really thin there. So what we're saying is this little distance right here is a distance dr, and the distance to the inside of this circle is r. And then that means the distance to the outside of the circle is r plus dr. Okay. Now that really is a circle with a circle cut out of it. So technically, just for the record, I will show you that the area of that dA is actually equal to pi times r, or excuse me, I should use lowercase here. Pi times r plus dr, oops, squared minus pi times r squared. Do y'all see how that's the formula for a circle cut out of a circle? Everybody understands the geometry that we're talking about there, r plus dr, and then that whole quantity squared, and then pi times r squared. Everybody get that? Anybody have any questions on that? Okay, I'm going to work this out, and I'm going to get the result that you're used to from Calc 2 and maybe late Calc 1, but I'm going to show you why that value is acceptable. So I'm going to factor out the common factor of pi, and then I'm going to square the binomial r plus dr. That's going to be r squared plus 2r dr plus dr squared. That's just how we, square a binomial. It's the FOIL method, but it's the FOIL where I've already combined the O and the I in FOIL. And then this will be minus r squared. So you see the r squared here is going to cancel out with the r squared here. which is kind of neat all by itself. But now that I've got that, I will have the formula is 2 pi r dr plus, now you can see it's pi dr squared. Now, what we normally write this as in the math and physics world is we'd say 2 pi r dr plus O dr squared. So what that means is plus terms on the order of dr squared. And remember, a integral is a Riemann sum. And that Riemann sum is supposed to be taken such that dr, the little width of the individual Riemann cube, or excuse me, Riemann rectangle, that's going to basically shrink down to infinitesimal. So, 10 to the negative 84th, for instance, is not an unreasonable dr, right? So if dr is that small, imagine how small dr squared would be. So if it was 10 to the negative 84th, dr squared would be 10 to the negative 168th. So you can see that that term is negligible. Okay, so that's why we're justified in saying the area of that little shape is 2 pi r, which notice that's the actual internal circumference. And then they're just taking that and multiplying it by dr, like you could expect to cut that that little circular ribbon there. You could cut it and it would lay out as a rectangle, and the rectangle would have a width of 2 pi r and a height of dr. But in fact, if you actually did that, it would actually look like this. Where this side from here to here would be 2 pi r. This side would be basically 1/2 dr. And this side would be 1/2 dr. And this thickness is dr. So you can figure out that this little triangle is 1/2 of dr squared. And this little triangle is 1/2 dr squared. Oh, actually, I forgot. Yeah, that's cool. I forgot a pi, but anyways, the main thing is that's actually what the shape is going to be. But you can see that those little triangles are all that we're losing. So hopefully this allows you to put some rest to your mind about the unsanctity or the what seems like a blatant disregard for reality when you call that area 2 pi r dr. Okay, I know I did when I first encountered it in calculus. And then when you work it out, you say, oh, okay, I understand now because it's on the order of dr squared. That should be fine. So that's going to be my differential area element. And in fact, that whole thing I'm going to call my dq. So what I'm going to do is I'm going to say this little guy is dq, and that dq is going to be sigma times dA, and that dA is going to be 2 pi r dr. Okay, not only that, sigma is going to be equal to charge over the area. That's what sigma is supposed to be. And of course, the whole disk, the charge is Q, and the whole area is pi r squared. So now I know what sigma is as well. Now, again, if I had taken that one little RD theta, RD theta dr, if I would have taken that one, I'd have a very clear answer to what R is. Here it's a little more complicated, but mind you, this distance right here is R, and the distance, let me use this, the distance right here is z, and those two are perpendicular to each other. So the total distance out here is going to be the square root of r squared plus z squared for this little dot right there. But it's also going to be that for this dot and 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 this dot. So I can actually say that v is going to be 1 over 4 pi epsilon naught integral sigma times 2 pi r dr. All of that's got to be divided by r, which we said was the square root of r squared plus z squared, like that. So now I can go ahead and integrate that. This time we have a dr as opposed to a d theta. So the denominator very much matters. What I'm going to do is I'm going to say, I'm going to erase a bunch of stuff because my iPad did it. I'm going to say let u equal r squared plus z squared, which means du is going to equal 2r dr. I've already got a 2r dr in there, so I'm good to go. I'm going to now call this sigma over 4 pi epsilon naught integral of, I'm going to put a pi up there too, because I just realized the pi was left there. Now all I have left is 2r dr, which is du, and then I have over u to the 1/2, which is the same thing as sigma over 4 epsilon naught times the integral of u to the negative 1/2 du. The integral of u to the negative 1/2, we take the negative 1/2 and add to it 2/2, and we get positive 1/2. And when we do that, we get negative 1/2 plus 1. Yes, that's going to be 2/2 minus 1/2, which would be positive 1/2. And then we got to divide it by positive 1/2. So this is going to become, dividing it by positive 1/2 is going to make the 4 become 2. And now I've got basically the square root of r squared plus z squared. And that's going to be evaluated from r equals 0 to big R. Any questions on that one? Okay, so when I go to compute this, I can say it's going to be sigma over 2 epsilon naught, which notice that sigma over 2 epsilon naught is what we ended up getting when we did Gauss's law for a plane. Okay, that comes in handy because remember, we do consider the option of where z is much, 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 much smaller than r, and then we get it's acting like a plane. But from this part, what we can get is evaluating r at r, I get the square root of r squared plus z squared minus, now I'm going to let r go to 0, and that would be the square root of just z squared, which is the absolute value of z. And it's the absolute value of z because it's the square root of z squared, but it's specifically the positive square root, so it has to be a positive. So we can do that, and we ultimately have it now, but this is the right answer, but it's in terms of sigma, and we were given q and r, not sigma. So now I'm going to go ahead and plug in what sigma is supposed to be, which we've already computed. So v is going to equal q over, now we have the 2 down there, so now it's going to be 2 pi epsilon naught and then big R squared. That's all just from the sigma. And then all of that times the square root of r squared plus z squared square root minus the absolute value of z. Now, at this point, what we're going to do is factor out a z. So I'm going to pretend like there's a z everywhere. It sort of is, but there really isn't. So on the top, I'm going to have qz. And on the bottom, I'm going to have 2 pi epsilon naught r squared. And then basically what happened is I factored out a z from the square root. And in so doing, basically I made a square root of r over z quantity squared plus 1. And then I made the absolute value just become 1. So that is an actual acceptable and neat answer for the voltage at P due to that disk. And like I said, for X or for Z much greater than R, we can actually show that it does work out to be the sigma over 2 epsilon naught, or you could even make it bigger by sigma over 4 pi r squared and some stuff like your book does. But anyways, the main answer is that. Anybody have any questions on that? Okay, so there's two where we actually had to calculate voltage given by using integrals. I think this is a good time to go ahead and take a break at 7:05. Let's come back at 7:15. I'll sit here the whole time, so you have plenty of time to ask me questions. But I'll start counting down at about 2 minutes till, but I'll be here the whole time. So everybody go ahead and take your break, and I will be here. and checking to see what time the actual debate is going. That's what it's. You kids are so well behaved. Well, I know half of you kids got put out on that fortunately. But did he?
Yeah.
Aw.
Yeah.
Well, Grace is a sweetie at least. And I'm sure he's a sweetie too. We got about 4 more minutes, everybody. Got about 1 minute, everybody. All right, it's just about time, everybody. Looks like everybody's here anyways. Anybody have any questions before we get started up again? I've got a couple more things we want to talk about in chapter 23, and then I'm just gonna call it a day. I can't really get much done in chapter 24 from this point. I guess I can do a little bit, but not much. So I'm not gonna do much, if any. So any questions? Oh. For the example photo, thank you. Gotcha. I'm looking up your question right now. Let's look on modules. I'm looking in, I clicked on modules on the left-hand side. Whoa, maybe this is the problem. I never shared it with you. Let's see if it's somewhere else. Or at least it's not where it's supposed to be. I tell you what, let me put it up there now. Jessica's here. She just walked around the side like she's trying to go outside. Let's see, in the create file, choose file. All right, I'm actually pulling it out of my files and putting it in there. I have it under a all semester use thing. Maybe it wasn't in my all semester use thing. Maybe it was just last semester. Yep, that's it. Okay, now if you look in the section called helpful documents and links, at the very top, there's something called ANONGOODMIRROR placement. And it's just a photo I just stuck up there. So it wasn't there before. I was wrong. Thank you for calling me out on that. And now it's corrected. Do you see it now, Ethan?
Yes, I see.
Okay. Sorry about that, everyone. I don't know. Maybe I sent it to the other class. I don't know. I don't know what happened to it. It's probably, I'll find it later. It'll be like in some random spot somewhere on Canvas. But anyways. All right. So what I wanted to bring us back to was this little idea of the dipole. So for instance, we already talked about an electric dipole, and an electric dipole can be represented by 2 point charges of opposite but equal charge values. So what I'm going to do is I'm going to draw a circle, and then I'm going to draw another circle, and I am going to say that this guy is the positive charge and this one's the negative charge. And what I'm going to also say is that this distance right here is D. Okay. And just so we'll know exactly what directions everything is supposed to point and all that good stuff, I'm going to imagine this for an instant to be in a specific coordinate system. And that way I can specify this dipole moment in terms of I hats, J hats, and K hats. So this is my y-axis. Notice the origin's actually at the positive molecule, the positive charge, and the distance d is the distance between them. And this guy right here has a charge of negative q, and this guy has a charge of positive q. Then what I'm seeing is the electric dipole moment is supposed to be Q times D, and it's a vector quantity, and it points in the opposite direction of the electric field that it creates. So if you imagine looking at this point, this positive and negative particle, imagine putting a positive particle between the two. If you put a positive particle somewhere between the positive one and the negative one, then it would be compelled to move to the right. It's going to move towards the negative charge. So that's the direction the electric field is to the right. So in this case, I actually want to do this just because it's going to be neater for you. So let's flip our positive and negative charges so I don't have a stupid negative sign in here. So what I'm going to do is take this and remove that plus and put a minus, and I'm going to take this and remove that plus, oops, remove that plus and put a minus. And now I'm going to make this into a plus, and I'm going to make that into a plus. So please do that. And here's the reason. I'm going to go back from from the scratch or the start, and I don't know, get my mixed metaphors up. Anyways, I'm going to go back and re-explain this. So if we were to put a positive charge between the positive and negative charges in this dipole, what we would now see is that the positive charge would be compelled to move away from the positive charge and towards the negative charge, which would be from right to left. So the actual electric field that the dipole is creating points to the left, which is the negative X direction. That's the whole reason that I switched it, is because now the dipole is supposed to point in the opposite direction of the electric field. So now I can just write QD I hat. That was the reason why I erased those signs and flipped them like I did. I apologize for that. But that's what the electric dipole moment is, okay? And your book goes so far as to give you some specific dipole moments. For instance, it says for H2O, and notice H2 tends to not be as strong at holding the extra electron as the oxygen does, because the oxygen adding that extra electron moves to a higher order noble gas configuration. But that dipole moment in coulombs times meters is P is equal to 6.1 times 10 to the negative 30th Coulomb meters. If you want to look at, for instance, hydrochloric acid, which has the formula HCl, then the H again tries to hold on to the positive, and the Cl basically steals the electron. And in this case, we get P is equal to 3.4 times 10 to the negative 30th Coulomb meters. NH3, the N actually wins at stealing the electron, and the H gets more positive again, H being sort of the weakest thing in there. In this case, we get 5.0 times 10 to the negative 30th Coulomb meters. They do a NH, which is 3. They do a CO, which is 8. That's enough. But the main thing is that's how we consider molecules. For instance, in an MRI device. In an MRI device, we actually will have our magnetic field, which is a very strong, on the order of a whole Tesla magnetic field, and it flips back and forth. And when it flips back and forth, it causes magnetic dipoles to do the same thing, or excuse me, magnetic and, for that matter, electric. It could, in principle, all depending on how, whether they're moving and that sort of stuff. But that flipping back and forth has a definite energy associated with one state versus the other, and from that you can get information about exactly what elements or compounds are present. So this is where that comes in handy. Now, with that in mind, your book wants to calculate what the actual electric potential due to a dipole is, and we've done this before with the electric field. And what I showed you was or what I at least mentioned to you was the dipole moment. The electric field created by it behaves a little weaker than the dipole, or excuse me, a little weaker than the electric field from a point particle. The reason being is the net charge of a dipole is 0. So the whatever electric field strength you get from the positive charge is trying to be subtracted from the negative charge. So what ends up happening is a point particle, for instance, has an electric field that goes like 1 over r squared, whereas a dipole has an electric field that falls off like 1 over r cubed. And of course, we know that a point particle had electric field 1 over r squared. And we just finished learning that it has a electric potential that goes like 1 over r. Well, guess what? The electric potential of a dipole goes like 1 over r squared. Again, another factor of r larger in the denominator. So I'm going to just go with that and use the diagram that your book has. So what you can imagine, for instance, is let's imagine a little, let's say it's a little negative charge right here. And let's say we have a little positive charge right here. Okay. That is a positive Q. And this is a negative Q, for instance. Now we're going to say the distance between them is, let's say, L. I didn't necessarily want to switch from D, but I'm using what the book had. And then I want to figure out at point P, what is the electric potential? So what we can do is we can imagine a line straight from here and then another line straight from here. And what's normally done is we imagine that there's a right triangle right here. And this right triangle has an angle associated with it of theta. And then this side has a length r, and this side has a length r, because that perpendicular line going across there forced them to have the same length, essentially. Now, when you do that, you can then compute the electric field, or excuse me, you can compute the voltage at P is equal to the voltage at P due to the positive charge plus the voltage at P, and that should have been like that, due to the negative charge. Luckily, this is a scalar quantity, so that's not too terribly hard to do. I can just say for the positive charge, I get Q over 4 pi epsilon naught times, in this case, the positive charge is just the distance r away. So I'm going to say Q over r. And then I'm going to say for the negative charge, it's going to be a negative Q. That's going to be over 4 pi epsilon naught. But this time the distance is r plus delta r, where this delta r is that little bit right there, which I think you can see is r cosine theta, or excuse me, is L cosine theta. Okay, because L is the hypotenuse and the delta r is actually touching the theta, so we know that's the adjacent. So that's L cosine theta. That's going to come in handy to us, by the way. So now that I have that, I can try to make some sense of it. Your book actually carries out the math. I'm going to skip it on this one, but ultimately we can say equals dot 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 equals dot dot dot, and you might even say a miracle. Whoa, we're not going to say a miracle because I just realized I was getting ready to misspell miracle. Okay, so we can say a miracle happens here. And what we're going to do with that miracle is we're actually going to just write down the results. And what your book gives us is that V ultimately is equal to 1 over 4 pi epsilon naught. All of that will be multiplied by Q times L cosine theta divided by R squared. Now, in this case, remember Q times L is actually the same thing as the dipole moment. So we can also write this as 1 over 4 pi epsilon naught times P cosine theta over r squared. But the main thing that I'm showing you here is that the voltage for a dipole moment, or the voltage for a dipole, sorry about that, is proportional to 1 over r squared, whereas v for a point particle is proportional to 1 over r. Okay, so that was the main result we're trying to get out of that. You can now, of course, use that formula as well, that v is equal to p cosine theta over r squared. I think I put that on the equation sheet. Does anybody have the equation sheet, or does anybody recall off the top of your head whether it had it? It doesn't matter too much if you do or don't. What's going to happen is when I go to make our next tests that involve chapter 23, if I don't have that on there, then I'm just not going to give you any questions with that. So that's the advantage. Okay. Now that I've done that, I can tell you that the next section is about determining the electric field from the voltage. And I've already given you a idea of how to do that. Specifically, I told you E is equal to the negative gradient of V. And gradient is an operator, and that operator, we write it as if it needs a space left to the right because it's supposed to act on something to the right. And then I write I hat partial derivative with respect to X, leaving a space, plus J hat partial with respect to Y, leaving a space, plus K hat partial with respect to Z, leaving a space. And that's what that is. So with that in mind, what we can do is now take our result for a ring and for a disk, and we can calculate what the electric field is. So what we found, for instance, for a ring was this formula right here, which is Q over 4 pi epsilon naught square root r squared plus z squared. So we had, for instance, V is equal to Q over 4 pi epsilon naught square root r squared plus z squared. Like that. Double check my math. Was that 4 pi epsilon naught, or was it 2 pi epsilon naught? It was 4 pi epsilon naught, it was Q, and it was square root of r squared plus z squared. Okay, so I got all that. So what we mean now is E sub z would equal the negative of the partial of V with respect to z. So I'm going to show you how to do that. Just pull the negative out in front. And in fact, I'm going to go ahead and pull the Q over the 4 pi epsilon naught. That's all going to come out in front. And now I'm going to take the derivative with respect to z of r squared plus z squared to the negative 1/2 power. And I wrote it that way because it's a little easier to differentiate that way. So now I have negative Q over 4 pi epsilon naught. Okay. And the derivative of anything raised to the negative 1/2 power is negative 1/2 times that same thing, which is r squared plus z squared, raised to the negative 1/2 minus 1, which would be negative 1/2 minus 2/2, which would be negative 3/2. And now I've got to take the derivative of the thing with respect to z, and that's r squared plus z squared. And the derivative of r squared plus z squared with respect to z is just 2z. So ultimately, you can see that the negatives cancel out, and I get, also you can see that the 2 here is going to cancel out with a 4 here and leave a 2 down there. So ultimately, I'm going to get E sub z, and this is for the ring. This is going to give me a positive Q over 2 pi epsilon naught times Z times R squared plus Z squared to the negative 3/2 power. And that should be it. Did I get a 2 and a negative? Oh, okay. Oopsie. That 4's got to come back. I canceled out one of the 2's, but I forgot there was yet another 2, so I got to put that 4 there. Everybody see that? I canceled out the 2 with the 2, but I still had this 2. So anyways, that is the result. And in fact, if you look back at your book, you will see that that is exactly equation. That one's equation. Oh no, that's example 2110. So, oops. So if you look back at example 2110, you'll see that we did an integral that was way more complicated, way more work, but we got exactly that same formula. So you can now go back and realize that, oh, I could do this much simpler integral that I did right here, and then take this very simple derivative that I did right here and get the same result that I did on the previous one. So that's something that's really nice, and it also closes the circle with how I told you you can always get back to stuff we used to get when we used vectors. There's one of them. Now we can also do the disk of charge. And for the disk of charge, we got a different result for the voltage. In fact, the voltage for the disk of charge turned out to be this nasty mess. So let me borrow this. I'm going to highlight it. I don't know. Is it showing you? It's showing there. Now I'm going to say copy. And pull it over to here. I'm going to say paste. And I'm going to put it right there. And I really don't need that box. That box is really aggravating me. So what I'm going to do is put that there, click off of it, and then erase the box. And part of the cube. I just took a little bit of his hair right off of him. All right. So now we've got the actual formula for the voltage. What I'm going to do now is move this to a more useful area. Cut, paste, boom. Okay. So now that I use that, I can see again, I have a Z. That's a possible way that could be helpful, but I think it might be a little nicer if I go ahead and multiply through by Z. That might actually work. So that's what I'm going to do. I'm going to say E. Whoa, Nelly, I want to start writing with the pen for starters. That might help. Okay. So I'm going to say E sub Z is equal to the negative partial of V with respect to Z. And this is going to be a negative of negative Q over 2 pi epsilon naught R squared. Now distributing that Z, I'm going to go ahead and say d by dz, this is the partial derivative part, of, when I put that z inside, I can put it inside the square root by squaring it, and I end up getting the square root of r squared plus z squared. And then, of course, when I hit the -1, technically I'm going to get the absolute value of z, because that's what it was supposed to be before. So I'm just going by memory. There's no way I would know to put the absolute value on there, but that's good enough. And we'll talk about that a little bit. So now I can take the derivative. I can see the two negatives are canceling out, and I'm going to get q over 2 pi epsilon naught r squared. And now I can take the derivative of something to the 1/2 power. So the derivative of something to the 1/2 power is 1/2 times that something to the 1/2 minus 1, which would be negative 1/2. So it's going to be to the negative 1/2 power. Yeah, 1/2 minus 2/2 is -1/2. And now I've got to take the derivative of that thing, which is r squared plus z squared with respect to z, which is going to be 2z. And now I've got to take the derivative of the absolute value of z. And the absolute value of z, if you actually made a plot of the absolute value of z versus z, you would see that basically it looks like this, and that's a 45-degree angle. So in this case, we were actually talking about some distance above a plane. There's really no difference between the formula you get for z and negative z. So we might as well just go ahead and pretend like it's a positive z. And the slope of that, of course, is 1. So the derivative of the absolute value of z would, in fact, just be +1. So now I'm going to get the negative that was already there times 1. And that's the formula that we determined for the electric field, the z component of the electric field above a disk. And I actually changed the bracketing I was using, so I'm going back to fix that. So now I'm going to try to simplify this a little bit more. I'm going to say E sub z is equal to, now in this case, we actually wanted it to be sort of in the opposite order. So I actually want to flip this. I think I had everything right, yeah. I wonder if I have my other formula backwards. Did I have z squared square root minus z? That looks like that did right. That was good. Oh, I'm checking something right quick. Yeah, so if y'all saw this, remember I copied this formula? Well, evidently I took part of that equal symbol, and that gave me what looked a lot like a negative. So I thought the two negatives canceled out, but that wasn't supposed to be a negative. So let me fix that right now. And let me fix that right now. Okay. And what that means is I'm now going to have this, whoa. What that means is I'm now going to have this negative out in front here, which I can get rid of by changing the order of subtraction. So I'm just going to say Q over 2 pi epsilon naught r squared. Now you can see the 1/2 and the 2 canceling each other out here. And this time it actually works out to be a good thing. And I'm going to get z, or excuse me, since I'm reversing the order, I first get 1, and then I get minus z over the square root of r squared plus z squared. And that is exactly the formula we got in example 2310. Not from 2310. That's the, I'm hoping I wrote it right, the right one before. I'm looking actually at your book and trying to see the examples that they did. Example 2113 and 21:7. Oops. So let me fix that wording right there. See examples 21:7 and 21:13. And when you do that, you'll see that again, we got exactly the right formula. So does anybody have any questions on that? All right. Well, I will tell you, chapter 24 is basically, let me stop sharing my screen for just a second. And let me start sharing my other screen for just a second. So when I look at chapter 24, I'm going to go over here. And notice we did skip some sections. We skipped the section on noise and digital transmission, digital binary numbers. All those things are really good to read, especially if you're going into double E or computer engineering or software engineering or hardware engineering, or if you're just interested in computer technology and stuff like that. All of these things are really good, including the oscilloscope and the electrocardiogram. But I'm jumping up to chapter 24, and this is on capacitance, dielectrics, and electric storage. If you ever happen to look in a circuit and you see something that looks like these little guys, these little, these chiclet looking things right here, and these circular chiclet looking things, and then these cylindrical looking things, those are almost always, if they've got two little wires sticking out of one end, they're almost always going to be a capacitor. And we're going to study capacitance next. And capacitance is defined to be basically the amount of charge an object can hold at a given voltage. So that the formula that's most important to us will be C is equal to Q over V. So that's where we're going. I definitely recommend you read that before we cover it on Monday, on Tuesday. Remember, I am going to put your online test and your face-to-face tests are both going to be online. I'm going to put your online test, which you can take at any time after I put it up. You can actually, that will be up by sometime tonight. And I'm going to give you until Sunday of next week to get it done. I'm also going to give you from Thursday morning, early, like 12:01 a.m., Thursday morning until Friday at 11:59 p.m. is the time where you can use. Hopefully you have a mirror and you can use that, but you're going to use Lockdown Browser and Respondus Monitor, and you can take the test at home, or you can set up an appointment with a testing center and they will accommodate you on any of those days. So make sure you get those done next week, but you're free to go. Thank you for coming, everybody, and I'll wait for the last person to leave in case anybody has any questions. Ooh, that was quick. Thank you, everybody. Bye-bye. Bye-bye. Oh, Carolina. Oh, Carolina. Again, and there we go.